I'll let her know.
I was a little self-conscious playing in the parking lot there and walking in.
Oh, yeah.
Like, oh boy.
Little suspect.
Yeah.
We saw you. Well, okay, very good. So we're going on 12-2. Hazel watched the video, so she can help us. Despicable Me, right?
Yeah.
Is it what's the direction and magnitude come from?
It's like one of the villains.
One of the villains
Yeah.
is his name Vector?
Yes. I think so. I think so. That would make sense.
And then he talks about direction and magnitude.
Yeah.
Okay, wow.
Okay.
Okay, we're not gonna watch
I
it.
think if I saw what it looked like, I'd totally
Yeah,
know.
we're not gonna watch it.
Ah.
No matter how much we pretend we don't know what it is. So, okay, so we are going to go on then to 12-2, which is algebraic representation of vectors. And in this algebraic representation of vectors, we're going to have two things, the component form of a vector, and then also the magnitude of a vector, which we already talked about, and some of this will just be a little bit of review. So let's talk about on an xy plane, let's say we have an a value here, we'll give it coordinates over whatever, over 3 up 4 is what a is, and then b, we'll say it's over 7 up 10, okay. And we'll call this b. So if we are to look at this as vector AB, what we know is that vector AB just means it's starting at A and going towards B, right? Mm-hmm. So you'd say, okay, vector AB like this. Now, when we do that, we're going to talk about two things. One is if I said, okay, here's vector AB, we know it's going from A up to B, we have the coordinates. If I said, what is the magnitude of AB? All right, so the magnitude of AB, that's just the distance of AB. Now, we were talking about with airplanes and stuff like that, that it's like, oh, it's traveling at 400 miles an hour. That was the magnitude given to us. But if this is what we have on a coordinate plane, the magnitude is just found by finding the distance from A to B, meaning it's just your distance formula. Mm-hmm. So some of these formulas, you talk about the magnitude, it's like, oh, I'm just doing the distance formula. So you would say 7 minus 3 squared plus 10 minus 4 squared, and you would end up with 4 squared is 16 plus 36, right? 10 minus 4 is 36. So 16 plus 36 is 52, I believe. And then that would be equal to 2 root 12. No, 2 root 13. I think.
Yeah,
2 root 13. So that's the magnitude of it. Nothing unique on that. Okay. Then we have what we would call the component form. And the component form is going to be of AB. The component form is equal to, well, let me put it down here underneath it. The component form essentially is like your slope. It's going to be what distance of x do I travel, what distance of y do I travel. Now it matters though if you're going from A to B and B to A, because if you're going from A to B, you would travel a positive x and then you would travel a positive y. So it actually matters. If you're going from B to A, you would travel a negative y and then a negative x, just in terms of like the y and x change. I mean, you would actually just travel down the line here, but the component form is referring to what's the change in x and what's the change in y. So how we look at this is important, meaning it is always going to be x2 minus x1, y2 minus y1, where the second x2, y2 is referring to the end letter you're going to or the end spot you're going to. And so you can just think through a picture and say, oh, well, how do I know which way to go? Well, if you're starting here, just make sure that you're going positive and positive. If you're starting here and going there, make sure you're going negative and negative. So you would get it wrong if you messed up the x's and the y's. So 7 minus 3 is 4, 10 minus 4 is 6. Now, one thing you can do is, as you're doing problems, if you're doing component form and magnitude, is we look at this, the 4 and the 6, right, x2 minus x1, that really is what our magnitude is, right? It's just a x2 minus x1 squared, y2 minus y1 squared. So if you find the component form of 4 and 6, then you can just go 4 squared plus 6 squared. Not that the math here is really hard, but the number here and the number here should match the number there and the number there. So for magnitude and component form. So this is not a coordinate point, even though 4, 6. This would be component form. What component form means is in a vector, it means, excuse me, I went over 4 and then I went up 6. That's what component form means. So you have component form there, you have magnitude there. What are some other things? And they'll ask you, there's not a notation, sorry, something in the eye. There's not a notation for component form. They'll just say, what is the component form of AB? They won't ask for, or there's not a notation versus what's the magnitude. If you see this, you know they're asking for the magnitude. So they'll say, find the component form and then find this. And what is this? This is magnitude. The component form, the other thing is that if you just have a vector coming from the origin, you know, like if they're referring to, let's say they say vector, whatever, u, and they're saying vector u is equal to, let's use some different numbers, but 2, 9. If they say vector u is 2, 9, and you're like, okay, well, how do I know? Because here I had an A and a B, I had 2 spots, right? 1 spot to start, 1 spot to end. If they give you something like that, the assumption is you're starting at the origin and then going like over 2, up 9, right? And then it's like, here is vector u, like that. That's vector u. So if they don't give you anything else, just assume it's starting at the origin of 0, 0, you know, which would then, this would be the component form. And then you can find the distance of that as well for the magnitude. They may say, hey, what's the magnitude of u? And you're like, well, I need a distance formula, so I need an x2 minus x1. Well, you're just going, 2 minus 0, 9 minus 0. So it's just 2 and 9 for that. Okay, so that talks about, I think, magnitude, component form, pretty straightforward. We gave that. Polar coordinates are given. Draw vector OP and its given component form. So here you're going to be given a polar form. Let's do, which one do we want? 8, 140. Okay. So you're given polar form, which you guys know what polar form is. Remember, this is not imaginary polar form. If it was imaginary polar form, what would it look like?
Something cis something.
Yeah, 8 cis 140, right? But so it's not imaginary, it's just 8, 140. So what they want is O is the origin, so they say draw OP and give its component form. So we're going to draw OP, where O is the origin, a little bit of what I just talked about, and then they want the component form. Now, remember, component form is just your distance of your x that you go and the distance of your y you go. That's what component form is. So when we go to draw this, hopefully we can draw 8, 140, right? We go over 140 degrees and then we go out 8. So we say, okay, there's 8, there's 140 degrees. So we drew, and then this would be O and this would be P, right? Technically, that would be vector OP starting at the origin. So we could draw it that way. So nothing unique there. It's just polar form. Now they say, hey, what's the component form? When you want component form, what are you looking for? You're looking for your x and you're looking for your y. Now in component form here, granted, if you think about this, you would say, well, I'm going a negative x and then up a positive y, right? So even though you think about it as a distance traveled and you're walking, you essentially, if you're going this direction, it will be a negative x and then a positive y. Because we're in which quadrant? Quadrant 2. Yeah, quadrant 2.
Yeah.
So, you know, here, kind of coming back to this one, it would be a negative x and a negative y because you're going from B to A, if that was the direction. But here you're going to have a negative x because you're in quadrant 2. So that also could where you have a negative x because it's a starting at the origin then going out a negative x up a positive y. So now we say, oh, well, how do I find x and y?
Like last chapter.
Yeah, just like last chapter, like,
So we could do sine. So we know that 40 is the measurable angle.
Nice, so we know that's 40 degrees.
So sine 40 equals y over 8.
Sine 40 equals y over 8. Is this a unit circle value?
No.
No. So what do we end up with? Y equals
8 sine 40.
Yeah, 8 sine 40, so it'll be in a decimal form. And we expect a y value out. Something less than 8.
5.14.
5.14 seems reasonable.
Yeah.
Less than 8, and it's positive. And then our other one would be...
oh yeah. 8 squared minus that squared.
Oh yeah, so you could do pi-fake theorem with that. So
Oh yeah, or just...
No, yeah, pi-fake theorem works good, or cosine of 40 is equal to
Yeah.
x over 8. Either way, pi-fake theorem, and just remember not to use rounded values in general. But either way, you could find x. You do pi-fake, or you get x equals. And when we do x, we expect a negative, well, actually, we expect a positive value because your calculator isn't going to give you the negative value, is it?
No.
No, because cosine of 40 on a calculator is going to be positive.
Yeah.
So your answer is positive, isn't it?
Yeah.
On your calculator, what did you get?
6.13.
6.13. So you have to be careful. You have to like think through where's the picture at. And so the component form, remember the component form is just going to be an x and a y. So if you write 6.13, 5.14, what that would represent is that you're starting at the origin, you're going a positive 6.13, a positive 5.14, putting you in quadrant 1. So what's the actual component form?
Negative 6.13.
Negative 6.13. So we have to be careful with our calculator, just knowing you have to know what quadrant we're in and then come up with that value. Questions there? Makes sense. You know, it's not too difficult. So again, component form is the new thing we are adding. Now, let's do this. U is equal to 3, 1. V equals negative 8, 4. Something like this. And let's go ahead and do a couple things like this. So they are going to ask you to, we'll just call this number 1 so I can separate it out. They're going to ask you to do some stuff like this. Let's say, hey, what is 2u plus v, let's say. So they want you to do 2u plus v. Now, you look at this and they are referring to u as like a vector. I mean, they don't write vector u, but they're like u is a vector. Again, a vector has to have a direction, right? And a magnitude. So, and you think about this, then vector u, and this is what I was referring to earlier, like that one with 2, 9. When we see u is equal to 3, 1, what we're really referring to is a vector that's going out 3, up 1. That's like its component form. So when we're adding vectors and we're multiplying 2 to the vector, things like that, what you can do is, this is essentially the component form and the component form when it's starting at the origin. So they're really, when they write 2u, you can, plus a negative 8, 4, right? What you do with vectors, and this is, I think they have some rules listed for you on page 427, which the rules are, we're going to do them here. You can multiply the 2 in. Now, when you take this 2 and you multiply it into the vector, it's called scalar multiplication. And you've heard that word before when you were doing matrices. And I referenced this with you, Walker, when we talked about matrices. Scalar multiplication, you see here that word, you're like, scalar multiplication. It's essentially distribution, but distribution is when you have things added or subtracted and you're distributed into an algebraic, basic algebraic expression. You've got, 2 times x plus 4, okay? All right, I distribute the 2 in and I get 2x plus 8, right? That's called distribution. Scalar multiplication, though, is essentially distribution, except for the fact that this stuff isn't being added. This is a component form, but the 2 is going to go into it. So scalar multiplication, just tell yourself, oh yeah, I'm simply doing a distribution. But the book will call it scalar multiplication, but I'm getting out 6 comma 2 plus a negative 8 comma 4. So scalar multiplication we just did, but also think of it as distribution. And so there's our scalar multiplication. And now with vector addition, with component form, you can just add your x's and add your y's. And so you will get a new component form, and so it will be negative 2 comma 6. And that would be the answer there. So not much, it's not complex math at all. It's just showing you how you can double your vector and then you can add vectors together using their component forms like that. Okay? Questions on that so far? It's pretty straightforward. Okay, then you'll have something like this. Let's erase this one. Where you can if A equals 0, 4, B equals 6, 1, find the coordinates of point P that is 2/3 of the way from A to B. Alright, so if A is 0, 4, B is 6, 1, find the coordinates of point P, which is 2/3 of the way from A to B. Okay. So one of the errors here on problems like this is that people are thinking they're thinking like distance stuff. And so you say, okay, A is 0, 4 over 0 up 4, right? And then over 6 up 1, 2, 3, 4, 5, 6 up 1. So okay, there's A, there's B, and you find the distance of that, and then you're like, okay, 2/3 of the distance, 2/3 of the distance from A to B, and you find out, okay, it's this long from here to here. We're not actually trying to find the length of it, we're actually trying to find the point that's 2/3 of the way from A to B. Okay, so what coordinate is there, not the distance. Okay, so when we think about this, we'll erase that. Essentially, let me erase this for a second. what we have here is A is equal to 0, 4. So that's actually not a coordinate point. It's kind of like U is equal to 3, 1. We're thinking of this as a vector. So A is equal to 0, 4, where it's starting at the origin going out. And then B is 6, 1, where it's essentially a vector, going, out to B as well. I'm not going to draw the line on that though. Okay. So then we want to find 2/3 of the way from A to B. So what if we have from A all the way down to B, we want to find the point P that is going to be somewhere like right there, right? So that point P is going to be 2/3 of the way from A down to B, going that direction. All right, so to go about this, we could use the idea of vectors, okay? So what we could think of this as is that, let's start with this. Find for me, what is the component form of vector AB? So AB, what's the component form of vector AB?
Negative 3, 6.
Negative 3, 6. Oh yeah, negative 3 for the y.
Oh yeah, sorry. 6, negative 3.
And then 6, okay, so 6, negative 3 for AB, right? Okay. So that's our component form of AB. What we can do is we can think of what would OP be equal to? Okay, now think with me here. OP would mean a vector going from O out to P, right? Now, if you think about that, the OP, anything going out, if I drew something out here, and this is O and this is whatever, we can use the letter P. But if I said OP is equal to, 8, 3, well, what would we know the coordinates of P are? What are the actual coordinates of P? If vector OP is 8, 3, what do I know the coordinates of P are?
8, 3.
8, 3, because it's starting at the origin. So the coordinates are actually the vector component form if it starts at the origin. So if I can find what OP is, whatever this is, then I can know what P is, the actual coordinates, because the coordinates are going to match what the component form is. So if you think about OP, though, vector OP in terms of a vectors being, if you will, added together, I think on whatever day that was that Friday?
Yeah.
I think.
Yeah.
Remember Friday, I talked about adding vectors together like this, and you can make a parallelogram. And so if I have, OP is made up of O to A, going like this way, A to P. If I go from O to A to P, what's the diagonal that I just created? OP. So if I go O to A to P, the diagonal that's created by this parallelogram, the resultant is OP. So what I know is that OP is actually made up of OA, right, plus AP. That's what not AB, I'm sorry, AP, like that. Putting this in terms of vectors. Now, with that, where's this or that? That's good and well. I actually know what OA is, right? What do I know OA is? Vector OA in terms of component form. We're not talking magnitude, right? We're just talking component form. What's vector OA?
0.
Not difficult. 0, 4, right? So OA is 0, 4. The issue is I don't know A to P because do I know what P is?
Oh.
No, however, I do know that if I extended this out, just like in the picture there, I could get from A to B. I actually know what AB is, right? What do we know AB is? 6, negative 3. Well, what do I know AP is in comparison to AB?
2/3 of it.
Yeah, so 2/3 of AB is the same thing as AP. AP is the same thing as 2/3 of AB. And do you know AB? We already, right? You established that AB was 6, negative 3, right? And so then we go, okay, 2/3 distributed in, what do we get? 0.4 plus 2/3 times 6, 2/3 times a negative 3. 4-1?
Yeah.
I believe. Seems pretty good. 2/3 times 6, and then 2/3 times a negative 3.
Oh.
4-1? Or no?
Wait, not 2/3 times negative 2?
Negative 2, I'm sorry. I was going 3 into the negative 1 is a negative 1. Negative 1 plus 2 is 1. Thank you.
That one's right.
This is one right. 3 goes into 6, 2. 2 times 2 is 4. 3 goes into this, negative 1. Negative 1 times 2 is negative 2. Now, we kind of check that, okay, going from A to P, you go out 4, down 2. Okay, good. That actually makes sense. Is that we're going to positive 4, down 2. Okay, to get to P. So now we just add our vectors. And we say, 0 and 4 is, oops, put 0 there. 0 and 4 is equal to 4. 4 and negative 2 is equal to 2. And now I know what OP is. OP is what? 4, 2. Therefore, I go, out 4, up 2 to get to P. And then therefore my coordinate P is going to be what? 4, comma 2. We'll do another one.
Yeah.
Yeah. So, and it'll follow the same process of what we just did. Let's do another one here. Let's say we have, well, pick one not coming from the origin. How about that? A is negative 3, negative 4. B is negative 6, negative 1. Oh, I'm sorry, negative 6, positive 1. Let's go negative 6, positive 1. Negative 3, negative 4, negative 6, 1. 1/6 of the way from A to B. Okay, 1/6 of the way from A to B. I'll give you just a minute to kind of set it up, see if you can set it up a little bit, and then we'll go forward. Same idea, same concepts. I'm in attendance here.
Mr. Wilson, will the vector we're finding always come from the origin?
Yep.
Okay.
Yeah, in these cases.
Yeah.
So we're trying to find the point, I didn't write the point P, but that's fine.
Mm-hmm.
You're trying to find the point P that's 1/6 of the way from A to B.
Yeah.
What do we get for a component form of AB? Did we do that?
Mm-hmm. -3, -5.
-3.
Oh, wait. 3, -5. Oh no, -3, 5.
-3, 5.
Yeah.
That would make sense. Not.
Oh wait. Isn't B's positive?
Positive
-6
one, I'm
positive?
sorry, I drew it as a -1, but it's positive one up there. Yeah, so there we go.
Okay.
Making a couple errors. There we go. So there's B, and then, yep, so -3, 5, that makes sense. So then, what did we do? Did we draw like something out there
Mm-hmm.
and then call that P?
Yep.
So OP, last time, we said OP, we kind of had the picture already from 0 to A, then down to there, right? So here, OP, what makes up OP? Well, OP is made up of, like, vector what?
OA plus AP.
OA
Or plus OP. Oh no, AP.
So OA plus AP. So OP is made up of OA plus AP. And if you drew a parallelogram like that, it would be the diagonal across.
Oh yeah.
So, okay, but then since we don't have P, but we do know that AP is the same thing as what?
-3, 5.
That's AB 1/6 of.
Oh, yeah, 1/6.
I'm sorry. Let's not do the numerical value. 1/6 of AB.
Yeah.
And then OA, even though they didn't give us OA, we do know it, right?
Mm-hmm.
OA is -3, -4,
Yeah.
plus 1/6 of -3, 5. And then we distribute scalar multiplication,
Mm-hmm.
and then add, and what do we end up with?
So we can just add the x and the y, right?
Yeah, when we do this, we just add the x's and the y's. So it's a -3 plus a
-1/2.
-1/2. So it'd be -3.5.
Yeah.
So -7/2 or -3.5.
Yep.
Then -4 plus 5/6.
Mm-hmm.
So that would end up being,
19/6.
what is it?
19/6.
19/6, -19/6. Seems reasonable.
Yeah.
Okay, and that then, therefore, there is your point P. Because that's going O to P, therefore that is P. Which,
Oh, yeah.
on the graph, that makes sense. The negative this and the negative this, so visually it makes enough sense. Okay, you'll have a couple problems about some classic problems, which I'll let you work through. But a box on a ramp and so with that, and so I'll draw, this is like number whatever, I think it is number 22 or something. But they have, you know, you have a ramp which can be drawn like a triangle, right?
Yeah.
And then you have a box sitting on the ramp like this, and here it's, you know, center of gravity, and it asks for certain things, like it says, okay, here's, you have a 50-pound box, 20-degree angle with the ground, so, you know, this is 20 degrees, this box is 50 pounds, and so then what it's going to ask for, a couple things, it says the component, find the component of the 50-pound force that is parallel to the ramp, and then find the component that is perpendicular to the ramp. What they're referring to is what's the component form that's parallel to the ramp, meaning how much of the 50-pound box weight is pushing down the ramp versus how much of the 50-pound weight is perpendicular, right? So perpendicular would be like this, coming down like this. So you have like this, and you have this, and then you would have the weight of the box, you know, going down like this, which, you know, you'd have to, now I drew the picture kind of poorly because it's a 20-degree angle. So if you think about it, at a 20-degree angle, do you have more weight of the box pushing down the ramp, or more weight of the box pushing like this way, even though the picture's poor? Is it, you have more weight coming perpendicular, right? Because it's, you know, a 20-degree ramp would look more like this, right? So, and you have this box, so that would probably be a better representation where you're thinking, oh yeah, I don't have nearly as much force, if you will, going that way versus the, you know, versus the perpendicular going out that way. So it's like, okay, nice, if I have more force going out this way, the box is gonna hold a little bit, or it may hold permanently, who knows, you know? And then at some point the friction is going to force it, or the friction loss is going to force it down, which, you know, we're not doing the physics on it. But when you end up drawing something like this force is greater than this force, so maybe your picture, you know, don't just draw like a line like that and a line like this. This would represent like a force going this way, which is less than the force going this way, and then you have the force going down, which would be your, you know, if you think about it, that's going to be some sort of your diagonal, like, right, your component of the vectors. So think through that. It can be a challenging problem, but it's good to kind of try to work through and understand this is like whatever, call this your x, this is your y, and then what's the component form going straight down from the box? You do know that force going straight down, because you do know the force of the box going down. What is it? I mean, oh, I'm sorry, you don't know what problem I'm looking at, so. And I didn't write the number up there, I put 20 degrees, but it's a 50-pound box lying on the ramp.
Okay.
So how much of that is going down?
All of it?
Then, yeah, you'd have 50 pounds of force, you know, going down, and then, you know, some amount of force that way and some amount of force this way.
Okay.
So you can think through it like
Yeah.
that.
Mm-hmm.
Then, well, this stays the same, right? That stays the same. But it was interesting, yesterday I saw with my father-in-law roof, and we got up on, you know, so it's like this, got up on the first, so we got a ladder going up to here, got onto this portion of the roof. Then the next portion is like this super steep, and then like this, and then, you know, then this was the peak. And so going up here is no problem. Put a ladder, hop on this, and then you move up here, and then we put another ladder. Well, this other ladder here, you know, is coming down like this and then landing here. Well, when you initially get on, the force acting on here was such that the ladder doesn't move, but as you step up towards the top, on a sliding surface, in the ground here, you do get a little bit of a push back, but because it's stuck in the ground, you don't realize that, like but there is, as you go farther up this ladder, you're changing your force, the gravity, if you will, the center of gravity is changing as you get higher up the ladder. So as he got higher up the ladder, he had more, if you will, more force going in this direction or farther up, therefore pushing the ladder back out. But I was standing there to protect him, keeping the ladder from sliding out. But so, anyways, that's a side note. So you'll get to that problem and you'll think through it that way. 50 pounds coming down, but then you have some amount of force going out that way, some amount of force going down the other way. Okay, you need some homework, problems, if you choose so to accept. With will, this is 12.2. We're going to go 1 through 17 odd, 21 through 24 all. So numbers 1 through 17 odd, Bob. And numbers 21 through 24 all. 12.2. We'll make 12.1 due on, well, I guess I'm going to say Tuesday.
Are they on this?
What? No, we're not. We will be here.
Oh yeah.
Will you be here Wednesday?
Yeah.
You're not gone all day?